today what I want to do is I want to basically start talking about the material we need to know for the next lab, which is called a multimeter skill demonstration. So in order for us to be able to do that skill demonstration, we have to go through the material in chapter 27, which is a fairly straightforward chapter. So I figured this is a good place to cover it and to do it in the lab. So I need you to read chapter 27. I would read maybe half of it this week and half of it next week. You don't have to read it all at once, and there will be a homework assignment in WebAssign associated with this later on. But I need to talk about the material now so that way you get to understand how to wire a circuit. There's a lot of YouTube videos on wiring circuits, and there's a great one. I can't put the link on Canvas because of it's not well captioned, but and I've mentioned this one person before. If you search series and parallel, so I'll tell you here. And the person's channel is called Electro. He makes the learning fun. He makes it fun. So he's a funny guy. He talks about building circuits. So if you search for this, go ahead and look at his video. And I'll give you a link to one of our videos. Tyler, our IA, made a video on one that's just specifically for this lab. I'll give you the link later. But yeah, anyway, if you do a search for series and parallel and type this person's channel in your search on YouTube, you'll find the video. Okay. And again, because it's not captioned, I can't really put the link in the modules. Okay. I guess before I get started, do you have any questions regarding the properties of charge lab? Okay. So let me move on then. So our goal today is really to discuss how we get electrons to move in a conductor, and really what I'm going to be focusing on is how to get electrons to move through a wire and how to make measurements that characterize what's happening in the wire or in the conductor. So we're going to be looking at trying to get electrons to move through here. I should say the unit that we're on right now in the lecture really focuses on electrons that are not moving. This lab, though, is part of the next unit, and it focuses on electrons that are moving in a conductor. Okay, and the reason why I have to do this lab now is because there's several labs we're doing this semester that require wiring. By the way, thank you, Aiden, for the video title. Okay, so let me lecture on chapter 27. I guess the first thing to ask is, suppose I have a conductor, a wire. What causes the charge to flow in the wire? What do you need to make the electrons flow? Well, what you need is an electric field. You need an electric field to make the electrons flow in the wire. And I think, we left off the other day in lecture talking about the kinematics of what the electric field does to charged particles. What I'm about to say will work for both negative and positively charged particles, but in a wire, when we get stuff moving through a wire, it's the electrons that are moving through the wire. So, if you remember the other day, we wrote down this equation So if you put a charged particle in an electric field, it's going to experience an acceleration. And so all we need is to have an electric field between the ends of the wire. So we need to produce an electric field I'm being more specific than just saying wire. So how do we produce the electric field? Well, the device that does it is a battery. There's also a power supply, but let's just focus on the battery for now. Okay. What does the battery do? A battery does work on the charges, and the work done by the battery gives the electrons in the conductor kinetic energy. So the work done by the battery ends up equal to the change in kinetic energy of the electrons. Okay. The work done by the battery. So what the battery does, it acts like, for example, I'll give you an analog. Let's say I have this marker. I take this marker and lift it from my hand to some higher elevation. I'm external to the Earth marker system, and so what I've done is I've done work on it and given it potential energy. What the battery does is it gives the charges potential energy. Okay. The electric field in the wire does work on it. So the work done by the electric field gives it potential energy. Now, here's the thing. The work done by the field is independent of the path, just like gravity. As a result, we can define the potential energy. Okay. So the work done by the electric field is minus delta U. In the same way we described the work done by gravity. The work done by gravity is minus delta U. And so oops, sorry, not the work done by the battery. The work done by the battery is delta U. The work done by the electric field is minus delta U. So the battery stores energy in the system so that it can do work, the field can do work, or the battery can do work on the electrons, giving them kinetic energy. So the battery is external to the wire, it does work on the system, giving the electrons in the wire potential energy, and that potential energy is converted into kinetic energy as the electrons go through the wire. Normally, what we do is we talk about the electric potential energy per unit charge. Okay. Which is delta U over Q. We describe the battery in terms of how much electrical potential energy a single charge gets. And the units of this is the joule per coulomb, also known as the volt. So delta U over Q is defined as delta V, which is called the electrical potential difference also known as the PD, also known as the voltage. So delta V is the electrical potential difference. It's the work or the energy, electrical potential energy per unit charge. It's related to the work per unit charge that the battery does. And so batteries are rated in terms of the electrical potential difference between the two terminals. So a battery maintains a delta V between its two terminals. Now we're going to deal with this more deeply when we get to chapter 25. Okay, so I'm going to say this again when we get to chapter 25. So I just want to say, to get the electrons moving through a wire, you need to produce an electric field. That electric field is really produced by an electrical potential difference. As long as you have a wire and the potential changes along the wire, you have an electric field. If you have a potential gradient along the wire, you have an electric field. Potential gradient, you can think of like pressure difference. You know, what causes a wind? What causes the wind outside? It's not pressure, but it's pressure difference. The pressure difference produces a force on the air, which causes the air to flow. So you can think of, analogously, the electrical potential gradient is what causes the electrons to flow. It produces the electric field. So if you have a potential gradient between the two ends of the wire, the electrons are going to move in the wire. Any questions on what I've said so far?
I have a question.
Sure.
Can you go over why the work done by a field is negative delta U, like for the negative?
Oh, it's by definition, right? I mean, that's what we did in, that's how we define the electric potential difference in 205, right? When I lift an object from my hand to some height above my hand, the work done by gravity is the negative of the change in gravitational potential energy. Isn't that true?
Yes, okay.
So it's the same, we're using the same definition.
Mm-hmm.
Yeah, and that always bothers people. Why do we use the minus sign? Okay. Other questions? Oh, why does the electric potential difference equal? It's not equal to the potential energy. It's the potential energy per unit charge, Kathleen. The electrical potential difference is the electrical potential energy per unit charge. So it's delta U over Q. That's how we define it. So, you know, this is a defined quantity for us. And then we look at, you know, what does this mean after this, you know, once we define this, what does this mean? Is that okay, Kathleen? Okay. All right. So the delta V is what makes the electron move through the wire. Okay, you can think of it as, it just pushes the electrons through. Some people want to use it as, I mean, a good analogy, if you want to use analogies to understand electric current, because it's hard to understand electric current and what happens in a wire, because you can't see what's going on. Think of water flowing through a pipe. The water pressure in your pipe that makes the water flow, or the pressure difference that makes the water flow, that's the same, that's analogous to the delta V in a circuit. So we can use the analogies. I mean, they don't always work perfectly, but we can use the analogies of water flow in a pipe to understand what is going on in a wire or in a conductor. Okay, so we will characterize a circuit based on how big of a push we're putting on the electrons, and basically how big of a delta V is across some element in a circuit, whether it's a wire or some other device. Make sense? So this is one of the things we're going to characterize. The other thing we're going to use to characterize is the amount of charge, and I'll write this down. the amount of charge flowing per unit time. Yeah, let me rewrite that. The amount of charge per unit time flowing through any point in a circuit we call the electric current. That's how I'm going to define it. And so we use the letter I for the electric current, not C before I, because that would be confusing with coulombs and all that. And the charge per unit of time, I would take the limit, because if I want to know it instantaneously, the limit is delta T goes to 0 of delta Q over delta T. Delta Q is the amount of charge that passes through a point in a unit time. And so this is dq dt. Of course, if I is current, which is the case in circuits that involve a battery, then we can say that I is delta Q over delta T for steady currents, meaning time independent. The units are coulombs per second, also known as the amp or the ampere. And it turns out that the amp is kind of a large unit for electrical current. And so more typical values or more typical currents that we encounter are milliamps. 1 milliamp is 10 to the minus 3 amps. 1 microamp, 10 to the minus 6 amps. Okay. When you have something running 10 amps, we're talking about a substantial electrical device like a refrigerator. Okay. 10 amps is a lot of current. So I should mention that there's a document on Canvas called the fatal current. You should read that. It talks about what electrical current is required to go through your body to kill you. If you end up getting 100 milliamps through your body, that's lethal. Okay, it's not a lot of current. Of course, your body has a large resistance to that current, so it takes quite a bit to get 100 milliamps through your body. Okay. What happens is when you reach a certain point, I forget the number, maybe 10 milliamps. If you actually start getting like 10 milliamps through your body, your muscles start to contract. And when you get to like 50 milliamps, your muscles contract so much you can't, if you grab on a wire, you won't be able to let go. You get to 100 milliamps, it's actually 75 to 100 milliamps, that'll kill you. When you get to 1 amp, most likely that might not kill you, but then you start cooking. So Tyler made a video for us, and I'll show you the video at some point. It shows you what happens when you run over an amp through something. We're going to run an amp through a hot dog. And you'll see what happens to it. Within a minute, it's ready to eat. Okay. What level? The taser uses a smaller current. It's not going to use 100 milliamps because that'll kill you, but it's a high voltage too. It's high voltage, low current, but it's enough of a volt. It's the right combination that it will knock you out. It won't kill you. And I don't know the numbers, but it's set up, but it's set up that it'll essentially knock you out. Now, some people have been killed by them. It's because everybody has different tolerance to electrical current. So if you run that taser long enough, it can cause pretty serious harm. What happens when you get electrical current go through your body, if the current's high enough, it gets your body, your heart going to ventricular fibrillation. You get an irregular, your heart doesn't beat right. When you get to this current, your heart is really messed up. Okay, it's worse with AC current because AC current changes direction at about the same rate as which your heart beats. So AC current is actually worse. We will not be working with currents that's going to kill you in this lab, especially since you're doing the labs at home. The currents you'll be dealing with are it's either the currents are going to be low or the voltages are going to be too low to harm you. I mean, when we're going to do an Ohm's law lab where the currents will be a little high, but the voltage is like 3 volts, it ain't going to kill you. If you ever want to feel what an electrical shock feels like, take a 9-volt battery, you know, those transistor batteries, and just put put your tongue on the electrodes. You'll feel a small shock. Okay, it's crazy stuff kids do, I guess, when they're small. Okay, so let me continue. So far we have the two things that characterize an electric circuit: current and voltage. There's really one more thing. And the other thing that characterizes the circuit is really the properties of the conductor. How does the conductor oppose current? So we'll talk about that too. Oops. So let me give you some examples of electrical current. These are actual examples of electrical current. You can have electrons flowing through a wire. You can have a beam of positively or negatively charged particle from an accelerator. Or those of you who do chemistry, you can have an electrical solution consisting of both positive and negative charges. They can produce a current. We're mainly going to focus on electrons flowing through a wire in our class. If you work on an accelerator, obviously you're going to consider a beam of particles. So if you're a physics major, you might end up working on an accelerator. Chemists might look, if chemists do electrochemistry, they will look at electrolytic solutions. Now, I should note to you that when we talk about an electric current, when we talk about this, whether a positive charge is moving to the left or a negative charge is moving to the right, they represent the same thing. Physically, I mean, electrically, it's the same thing. Whether an atom loses a negative charge or gains a positive charge, physically, that's the same thing. At least from the electrical point of view. Now, granted, the mass is different, but does that make sense? Normally, I show video illustrating this, but because of copyright issues, I'm videoing this online. I try to avoid showing it, but I also have issues with my computer showing videos. So I'm going to skip this video. I have too many things running on my computer and it doesn't work. So, because of this, it doesn't matter whether we talk about electrons moving in one direction or conventional flow in another. So let me illustrate that. If I have a battery, so let me draw a battery. This is not the traditional symbol for a battery, and this is going to be, I'm going to put a light bulb in my picture. The one I've drawn in the PowerPoint notes is not really a good drawing. So let's say I have a light bulb. I need to have something in there, otherwise I'm going to have a direct short. When people studied circuits many, many years ago, they thought, oh, it's positive charge moving this way in a circuit that's causing the light bulb to glow. And they called that conventional current. It wasn't until later that it was discovered that really it's the electrons that are flowing in the other direction. Because only the electrons can move, the positive charge can't move in the material. So it's the electrons that are flowing in the circuit. However, when you analyze a circuit, it really doesn't matter whether you say positive charge is moving or negative charge is moving. It makes no difference. When you're measuring current and you're talking about electrical potential difference, it doesn't matter whether you're talking about positive charge, this side losing positive charge, or this side losing negative charge. It's physically the same thing. I tend to use conventional current flow, even though it's really electrons that are flowing in the wire. By the way, I should mention something. Your book points this out. And I make this mistake a lot. We're talking about charge flow. Okay? Current is charge flow. But a lot of times we say this term. We say this all the time. Physicists say this all the time, and I will say it too. You'll catch me saying this. This is redundant because current is charge flow. Okay, current is charge flow, and then you say current flow. So it's kind of redundant. Your book talks about that. Okay, so saying current flow is a redundant term, but I don't know, just hard to avoid saying that. Okay, so if we have a wire, so here's a picture of a wire. Here's a cross section of a wire. And when I talk about the amount of charge per unit of time going through the wire, I'm really looking at the amount of charge going through this cross section of a wire. That's the electric current. Okay, that's the electric current. Analogously, if you want to measure, if you talk about the amount of water flowing through a pipe, the current of water going through a pipe, you can easily measure that by turning on your water hose, collecting a certain amount of water in a bucket for a minute, and then take the amount of water you have, dividing by 60 seconds. That'll tell you your water flow. Okay. The same idea, except we're talking about electrons instead of water flow. We're talking about electron flow as compared to water flow. We can quickly come up with an equation that describes electric current. Imagine I consider a bunch of electrons flowing from this point in a wire to this point in a wire. Let's imagine that the electrons, on average, are moving with some velocity v sub d. V sub d we will call the drift velocity. In a time delta t, the electrons that started here and go to here, they will travel this distance. And we'll call that D, or we'll call that L. How do I characterize the electric current using this, just a simple idea? Well, I want to know how much volume is in here. How much volume swept out? By moving charges. That's going to be the area of the wire times L. And if I know the number of charge carriers per unit volume, then the number of charges I have So how do I figure out the total charge? Well, if all these particles in here that go from here to here have charge Q, then the total charge is Q A V sub D delta T times N. And so what's my current? My current is, I'm assuming the current's constant, okay, so I'm not going to take a derivative. I'm just going to take delta Q over delta T. So this implies that I is equal to Q A V sub D times N. So that's how we can quantify the current. Now watch this. Look at this term. I'll highlight them in red. Look at this term and this term. If you have a positive charge moving to the right or a negative charge moving to the left, you get the same current. Because what happens? Both sides change. Okay, so physically you can see that from that equation. Now this is not an accurate model. Why is what I did not an accurate model? Anybody want to guess? Why what I did here is not an accurate model? Well, it's because, well, first I assumed the current doesn't change anywhere along here. And really, this is an average value. So really, we can think of this as a definition for an average current, maybe. Okay, because this V sub D, I'm assuming, is constant. So really, I can think of this as an average value. If I really want to know it exactly at one point, I need more details. But this gives me an idea of what's going on in the wire, at least. This allows me to model it. And it shows me that a negative charge moving to the left is the same thing as a positive charge moving to the right. Now, next week, I'm going to make this a little bit more general. And we can also define one more thing. And again, this is not very general. I can define the current per unit area. I can take I and divide it by A, the current per area. I define it as J. And we have very similar concepts. When you talk about heat transfer, in Physics 215, you come up with very similar concepts, just the letters are different. Okay? And in this particular case, it's going to be Q V sub D times N. This is called the current density in your circuit, the charge per unit area. And of course, when we do circuits in our class, this is constant. But what happens if it's not constant? And I'll talk about that next week. Because when we talk about magnetic fields, we're going to look at the cases where this is not constant. And then we can do some calculations involving magnetic fields. So again, instantaneous current is dq dt, and so delta q, the amount of charge flowing through a certain point in the wire, is the integral of I dt. So just to give you an idea of how big the amp is, how many electrons is 1 amp? That's my question. How many electrons are in 1 amp? Okay, well, and now I'm going to erase this. One amp equal 1 coulomb per second. And I'm going to divide it by 1.6 times 10 to the minus 19 coulombs per electron. And so the coulombs will cancel. I'm going to get, can't spell, I'm going to get the electrons per second. This ends up being 6.3 times 10 to the 18th electrons per second. Okay, so you can tell, you know, the amp is a pretty big unit of current. So in a material, how are delta V and I related? If you do an experiment, of course the results are going to depend on the material, but if you do an experiment, there's a lot of materials if you measure the current going through it as a function of delta V, there's a lot of materials where the relationship is linear. And so we can say that I is proportional to delta V. The proportionality constant is called a resistance. This is a measure of opposition. Can you see that color, by the way? Is that okay, or is it too light? Is that too light? Yes, no? It's fine, okay. So it's a measure of opposition to current, the charge flow. Okay. Here's the thing. George Ohm, discovered this. So if this relationship holds, and R is independent of applied voltage, then the material obeys Ohm's law. So what a lot of people forget when they talk about Ohm's law, and even electrical engineers will forget this, not all of them, but some of them, that Ohm's law says that this relationship is linear And R is the same no matter what delta V is. The value of R is independent of delta V. That's what an ohmic material is. That's something that obeys Ohm's law. It obeys this equation, and R is independent of the applied voltage. That's Ohm's law. So there's a lot of materials that obey that principle. Do all materials obey that principle? No. I mean, look. I mean, you guys have studied Hooke's law. What's Hooke's law? Well, that represents the relationship between the force on the spring and how much you stretch it. What if you stretch the spring too much? What if you take a spring and you stretch it too much? What happens? You destroyed it, right? It ain't going to be. It's not going to be elastic anymore. Well, same thing with Hooke's law. There's a limitation to this. If you put too much of a voltage on the material, this won't be a straight line anymore. Okay. Furthermore, there are materials that don't obey Ohm's law. That's because they heat up. When materials start getting hot, if you put enough current through them, they'll actually start getting hot. A light bulb is like that. Light bulbs do not obey Ohm's law. And what I mean by that is that R does not stay constant. This equation is still valid for a light bulb. It's just that R is not constant. So in that graph, the green one, it says non-ohmic, that would be representative of a light bulb. So next week, not next week, in 2 weeks, you're going to do the Ohm's Law lab, and you'll look at a material that's ohmic, and you'll look at a material that's not ohmic. The non-ohmic one is actually going to look at two materials that are not ohmic. One's a light bulb, the other one's going to be a diode. Okay. So, what are the units for this thing? Well, R is units of volts per amp. Okay, volts per amp. Of course, since Ohm came up with the idea, these are all called ohms. And a symbol for it is the capital Greek letter omega. Typically, these are large values, so one kilo ohm is 10 to the third ohms. 1 megohm is 10 to the sixth ohms. There are devices that we use when we build circuits that obey Ohm's law. They're called resistors. My definition here is not super rigorous. Okay. Oops, that's a 1. Yeah, sorry. I don't know why I wrote 10. I think I even said 1, but then I wrote 10. I think I was going to write 10 to the third. Thanks, Ratesh. So there are devices, and we're going to use them in the Ohm's Law lab. For this lab, for the lab we're going to be doing, the multimeter lab, we're going to be using light bulbs. Okay, but you'll see devices using circuits that obey Ohm's law. And their job is to either limit current or to use them in combination with other resistors to give you a delta V that you need for something. Okay. So what I want to do now is talk about the building blocks of a circuit.
Professor?
Yes.
Are we ignoring the resistance in the wire which is used in the circuit?
That's a good question. That's a great question. So typically in a circuit, the values of the resistor are significantly higher than the resistance of the wire. So their resistance is going to be negligible.
Okay.
Okay, so we're going to assume that the resistance of the wire is going to be much smaller than the light bulb that's in your circuit or the resistor that's in your circuit. By the way, the resistor that's in your circuit or the light bulb that's in your circuit, they're given a special name by people. They call them loads. Because what they do is they suck up the electrical energy provided by the power supply or the battery. So we call them loads. And that's what you see in the picture.
Do they pull the electrons toward them?
Well, what happens, I mean, and this is something I'm going to talk about next week, but when the electrons are moving through a wire, basically they're continuously colliding with the atoms in your circuit. And when they do that, they dump energy into the wire or they dump energy into your load. So something that's more resistive, you can expect more collisions. So you're going to see more energy being dumped into the material. And so the energy will be converted into heat. Does that answer your question, Raftesh?
Yes. So can we like melt a wire with current?
Oh, absolutely.
Okay.
So wires,
I think I've seen, yeah.
Wires are rated for current. And so you can have a very, the smallest diameter wire can't take much of a current as opposed to like a thick wire. So like, when you go to a hardware store and you buy, those big utility wires, they're rated at various currents because the higher the current, the more energy is going to be dumped into the wire. So if you ever run a vacuum cleaner for a long time, feel the cable. It's warm. If you put too much current through them, it'll start melting. And that's why we have fuses in homes. But anyway, we'll talk about that later. But you have fuses in homes because if you run too much current in your wires, you'll melt the wires and start a fire. And I shouldn't say fuses, I should say circuit breakers nowadays. Okay, so let's take a look at this circuit. This is the simplest circuit you can have. So what are the parts of this thing? Well, there's the wires, there's the power supply. The resistor that you see there is called a load. And the green arrows are representing the electrons that are going through the wire. The EMF that you see there is the rating of the battery. But your load, your resistor, and that could be anything. It could be your light bulb, whatever that's hooked up to your power supply or your battery, okay, is not going to get the 3 volts. Because of the fact that your battery or your power supply has some sort of internal resistance built in. For a battery, that internal resistance gets bigger as the battery gets older. As that gets bigger, then the voltage across R gets smaller. And basically, if this R was a light bulb, the light bulb won't go on. And then you throw away you get rid of the battery. I should say you recycle the battery. So let me say a few things, because I haven't said anything about the symbols. So let me go back to the board. That's called a schematic diagram. And When we draw a schematic diagram, that's basically a diagram that represents the circuit. And when I draw them, I'm assuming, usually I'm going to assume things are ideal, except when I draw in the box around the power supply, showing that the power supply has internal resistance. But generally, I'm going to draw this for the battery. Okay, really, to be technically correct, this is one cell of a battery. A lot of times what people will do is write something like this. But physicists are not always careful in drawing their power supplies. Electricians and electrical engineers are much more careful. They have to be much more precise in drawing these. These are multiple cells. Or sometimes if you do this, that means a power supply. Okay. This is the symbol for a resistor. Because really the electrons are undergoing more collisions in the material as they go through the wires. And so I think that's why you choose that for the symbol for R. Okay. So let me say something about the internal resistance, because it used to bother me as a student as to what that means. The internal resistance just represents the effect of the chemical properties of the battery, or the power supply, the mechanical properties of the power supply. There's no real actual resistor in there. You draw that in there just to represent the effect of the chemical properties of the battery. And as that gets bigger, in other words, as your battery gets worse, the R gets bigger, and then the voltage across the load decreases. So the voltage across the load is not the EMF, but it's the terminal voltage. Okay, it's called a terminal voltage. So wiring a circuit like that is really not that bad. So let me show you. Let me switch cameras real quick. So this comes with your lab kit. So now you're going to be using your lab kit. This is in your lab kit. Okay. So I have pre-wired one side of the battery to this light bulb. I don't know if you can see that here. Okay. Then I'm going to take the other side of the battery and just connect it to the light bulb. You see it go on? Now, by the way, in order to do this lab, you need a screwdriver. So your kit should come with one of these. Okay, so you can actually screw the wires in place. So yeah, you're going to have to use screwdrivers. And let's see if I can screw this in. It's kind of tough to do. And I'm actually not doing it the proper way. I should actually be putting this the other direction. I don't have much space. The other problem is I'm left-handed. Anyway, I'll do that later. Oh, I'm wasting time. But anyway, you're going to have to screw that in when you're doing the lab. So that's a simple circuit. This battery and this light bulb. Okay. Let me switch back to the PowerPoint. Let me show you another, a different type of circuit. This is a circuit with two two load resistors. They can be these load resistors can both be light bulbs. And then I have the power supply, your battery. Okay, so what happens in this case? Let's pretend. Oops. Let's ignore this internal resistor, okay? And let's assume everything is ideal. When you look at the positive side of this battery, and you ignore this resistor, and the wire is ideal, this point in the circuit is tied to the 3 volts. This point in the circuit is tied to the 3 volts. The above point in the circuit is tied to the 3 volts. So the left-hand side of the 2 resistors are at 3 volts. And if I ground the negative side, and if I make it 0, then the right side of each is at 0. So the potential drop across each resistor is 3 volts. We say that they're in parallel. Some terminology, this closed path that you see in your circuit is called a loop. This circuit has 3 loops in it. Can you see them all? 1, 2, and then the big outside one. Let me go to the board and let me draw the idealized version of this circuit. I'm going to draw a light bulb instead of resistors. Let's make that 0 volts. Let's make that 3 volts. So this point here is at 3 volts. This point here is at 3 volts. This point here is at 0 volts. This point here is 0 volts. This point here is at 0 volts. So these two are both at 3 volts. And so we say the bulbs are in parallel. Okay. This point over here, where 2 or more wires join together, is called a node. Or another term is a junction. Let me check my time real quick. Okay, I'm running out of time. Okay, so let me change to the camera. And I'm going to wire these in parallel. I'm going to use the bottom bulb. Let's see if I can do this quickly without being clumsy. And I'm probably going to do it the incorrect way. Or actually, I'm going to do it this way. One of the problems I have is as I get older, it's hard to see these small things. Okay. So I'm going to, instead of using screwdriver, I'm going to connect one here. I'm going to wrap this around. Oops. And then I'm going to cheat. Let me grab a big wire. And then I'm going to connect these two together. So those bulbs are in parallel. Really what I need is another wire that goes from here to here, but I'm going to hold this in place so it's faster. I got that. When you do this at home, you can just use a screwdriver. And you guys have better eyes than I do. Okay, so that's a parallel circuit. Okay, so let me take the battery out. Okay, so that I don't use up the battery. Okay, one more item. So regarding circuits, let me change. Give me a second. That's not it. Can't cooperate. Okay. Let's look at this circuit. I have 3 batteries hooked up after the other, and I've labeled different points in my circuit. And this symbol here that you see, this symbol that you see here is called a ground. So I can reference this point A to 0. So remember, batteries are devices that maintain a delta V between their terminals. So this point is at 0 volts. This other side is at 1.5 volts. But because I directly connected the positive side of one battery to the negative side of the other, I have forced point B to be at 1.5 volts. And because the battery maintains a potential difference between its terminal, this second side has to be 1.5 volts above that. So let me go on the board and illustrate this. There are 3 separate cells. Let me change my view here. Oh, I got it. And so this point's at 0 volts. This point, 0 volts. This point over here, 1.5 volts. Because a wire connects from this terminal, the positive terminal of the battery, to this negative terminal of the battery, this is 1.5 volts. And this has to be 1.5 volts above it because it's a battery, so this is at 3 volts. And since the positive of this side is connected to the negative of this side, then this is at 3 volts. And this is at 4.5 volts. If you think about it, on the electron going through here, each time the electron goes through one of these, it picks up energy. The amount of energy is the value of the charge times this potential difference. So Q times 1.5 plus Q times 1.5 plus Q times 1.5 is going to give you 4.5 volts times Q. So each time you go through here, you pick up more kinetic energy. And guess what? The light bulb is going to be brighter. These power supplies are connected in series. Okay? Those power supplies are connected in series. And this will be brighter. Now, if you take two bulbs and put them in series, they look like this. You hook them up one after the other. Now, what's the difference between series and parallel? In order for you to have a circuit, you need to have a closed path. In order for the electrons to move through a circuit, you have to have a closed path. So, if I put 2 light bulbs in a circuit, guess what happens if this one dies? What happens if the bulb dies? What happens to my circuit? What happens to this bulb? It goes out. If this one goes out, they both go out. Because why? Because if this goes out, it's the same as if I broke my circuit. The electrons get here, and then they ask, okay, where do I go? I can't go anywhere. Okay, so in my circuit, point C is at 4.5 volts, and this is at 0 volts. So the potential difference between C and D is 4.5 volts. And the voltage is 4.5 volts. Okay, so I'm going to try to illustrate this for you. Wrong camera. Oh no, I got the right camera. Okay, so I'm going to try to connect two batteries in series. So I'm going to take, make sure I do this correctly. So right now I have the negative of this one connected to the bulb. I should have it the other way. I messed that up. Oh no, it's fine. I'm going to take the positive of this power supply and hook it up to the negative of the top one. And what I'm going to do is twist the wires. And then the positive of the top one, I don't know if you see how much brighter this is. You guys notice it's much brighter this time?
Yes.
Okay. Because I'm using two batteries in series. And if I put two light bulbs in series, then the light bulb will be dimmer. Because then I'm splitting the energy. I guess I'll do that later. Okay. So, I want to talk about making measurements. And let me switch this view. And I only have a minute. I want to just tell you how to make one measurement. In your lab kits, you got two devices that measure current, resistance, and voltage. You're going to have to learn how to use them. They're called multimeters. Okay? They're called multimeters. And you have to demonstrate to me that you know how to measure delta V, I, and R. This is the easiest thing to measure. This is the hardest. Why is it so important for you to be able to make these measurements? Why am I making you do this lab? Because you're going to be doing a lot of measurements this semester in the subsequent labs, and you especially need to make this measurement. Because if you do it wrong, you will blow the fuse in the multimeter. Meaning you need a new fuse. You got to contact Tyler or me to get a new fuse. Or you have to go to the hardware store and buy a new fuse. So you got two kinds. One's a cheap one and one's a little bit more expensive. Although they're both okay, I guess. Now this is a big one. And I really think you should use the smaller one for this lab. Okay, so there's two of them. The small one I have by the camera, on my other camera. They have manuals associated with them, and I think what I got to do is, because I ran out of time, next week I'll at the beginning of class, I will demonstrate how to use them. They're actually not, I mean, they look hard to use at the beginning, but they're not that hard. Okay, resistance is the easiest to measure. Measuring the opposition to a flowing current is the easiest to measure. And then the voltage is the second easiest. This one is the hardest. And if you don't do things right, you'll blow your fuse. And one of the things is I want you to get good at measuring current so that if you go to Pattingale's class, you're not blowing fuses in this class. Because you'll be using a lot of multimeters and circuits. They're very complex. Okay, so that's the goal, is to learn how to wire things without blowing the fuse. I had one semester in my career where the 210 class, nobody in the 210 class blew a fuse during the semester, which is pretty impressive. So, I guess I won't show you how to use the multimeter. I'll show you the assignment real quick. This is the assignment. There's 6 exercises you need to do to demonstrate to me that you know how to use the multimeter. Let me blow that up. And you have to film yourself carrying out all those steps. I kind of showed you some of them already in my video this morning. Okay. And it has a rubric. Now, just in case you have a hard time with this, because a lot of times students have issues, some difficulties doing this. There's something new, because you're actually learning a physical skill, okay? And you're really learning a physical skill here, in addition to an academic skill. So I want to show you under modules. Again, I got to switch views here. I have a link to a simulation. That you can use to build things, build your circuit. So you can use a battery and a light bulb, and you can use a wire, and you can build your circuit very quickly. Okay, or you can use a multimeter. You can throw in a multimeter and maybe measure voltage. I'll tell you the voltage. So I would practice with this. I would play around with this so you can get to see it work. Okay, so I threw this in for you so you can play with it, just to practice how to make measurements. And you can get as complicated as you want. You can throw switches in there, whatever. Okay, so I put this in for you so that you guys can get some practice. Because last semester students wanted some more resources, so that's one. I do have other resources, various links. These are videos. So you can watch these videos. Okay. So use the resources that I've given you so that you can do this exercise. This is going to be due March 7th, but I'm lecturing now so that we have enough time to cover this material. Okay, I've gone too long. Thank you for your time. I will see you in class later. I got to get ready for the 9:30 group.